So, we have looked at various processes which have been used for texturing multifilament yarns, and last time we did look at spun yarn texturing also, which was the bulk yarn, high bulk acrylic yarns. So, high bulk acrylic yarns we know can be produced by mixing two fibers, shrinkable, non-shrinkable, with a substantial differential shrinkage. So, the principle would be differential shrinkage principle, but there should be a substantial difference between the shrinkage. Then we did talk about the toe to top conversion, two basic principles, crush cut and stretch break. The twist levels in the unbulked yarn should be low to allow migration of fibers, because shrinkable component is supposed to migrate to core, at least towards the core of the yarn, and the non-shrinkable component would come out and be majorly responsible for the bulk generation. The bulking can be done by a batch or a continuous process separately, by steaming or any other dry heat that you may like to use, but it is possible to combine the process of bulking with dyeing, such as simultaneous dyeing and bulking can be done. So, we look at the texturing of spun yarns, the yarns which are already spun using staple fibers, and we want to get the same or similar effect, which means that we would have stretch and bulk. So, twist texturing of spun yarns. So, the difference between the previous ones is the spun yarns are made from staple fibers. We were working on filament yarns, twist texturing is concerned, and they are definitely not parallel bundles of fiber, they are already twisted material. So, what do we do? If we do the same process at twist, detwist, untwist, so there is a possibility that you may actually over twist, because a normal spun yarn has got enough twist for all the properties that you desire. Going beyond that optimum can either make it very highly of a nature which is snarling nature, or may break fibers. So, how do we twist more? So, this has to be different than what we have been doing before, because it is neither a filament and nor a parallel bundle. So, what is the alternative? The alternative could be that you ply or double, take two yarns and then twist the ply, give them a ply twist. So, that you can give the ply twist of whatever desirable level based on the denier of the yarn, and untwist after setting. So, this could be the one. We cannot probably use a single spun yarn and do similar things. We may also not be interested in having too many spun yarns, let us say 10 spun yarns being twisted together. The denier is too high and it may or may not say. So, what people have tried is taking a double yarn, giving a ply twist, and then do whatever you were doing. So, this structure will be, if it is a twist texturing, will be different in the sense that There are only two yarns which probably may have whatever structures that they can have, and not many yarns. And therefore, if you are looking at the bulk generation, it will be there because it is still a yarn. The denier of any spun yarn is not going to be small, it is not like a denier of per filament of a filament yarn, it will be much larger, and therefore, you will get the coils in a twisted structure, but then we are saying that there are only two yarns likely to be there. And so, these yarns are obviously wrapping over each other when they are twisting, right. So, this is two yarns wrapping over each other, not more than that. And so, this structure is like slightly different, but it will still be helical because you have given a twist. The same type of migration effects we will not see here. We do not expect in applied twist the fibers from one yarn are going to migrate to the other yarn. It does not happen. So, those type of things will not happen, but at least they are going to be wrapping over, and so in 3-dimensional space you will be able to get a helical structure. So, spun yarns are available of all types, the thermoplastic ones like polyesters, polypropylenes, and non-thermoplastic you have all kinds of natural fibers that we have, they are also available. So, what we are looking at in possibility of texturizing these things, and yarns are also available as blends. So, you can have a polyester viscose, polyester cotton type of blend also. So, now you have another opportunity getting created where either the thermoplastic nature could be used in blends and do not use anything else, or use mechanisms to set the non-thermoplastic part also. So, if there are thermoplastic fibers, so you give a ply twist, then you set and then detwist. So, this is the same type of a process which we understood otherwise was a Helenka process or a false twist process. So, one can use and employ these processes, Helenka being a batch process, it can be used, a false twist is a continuous process, this can be used, and the setting will be done by heat, and therefore, this process should be considered as a thermomechanical texturing. So, as a principle it is the same thing, all those setting by release of energy principles are involved. So, although you will be having generally two spun yarns plied together and then heat set and then detwisting, and you will get similar retraction properties because you are now setting this process. If we look at the non-thermoplastics, so any material can be used, but a good amount of work was done on cotton, viscose, some amount on wool, and in some different senses, if you consider as a high bulk material, so jute, polypropylene combinations have also been done, which are also, as we said earlier, they are spun yarns. But definitely there was an interest in this, a good amount of research papers were published. We cannot say that they are commercially successful and people are now using them, but interest has been there, and reasonable properties also were obtained from the bulk and stretch point of view. So, process will be the same. Here also take two yarns, give them a plied twist of an appropriate value and set and detwist. Only thing is, now the setting may not be thermomechanical, but may be thermo-chemo-mechanical, or you can call it thermochemical setting. So, mechanics anyway will come because you are twisting. So, it is in a way either a thermochemical, that is, you may be requiring some heat as well to do the process, or it may be simply a chemo-mechanical. If your systems can work at room temperature. But invariably we might just say that it may be thermo-chemo-mechanical texturing. So, one important thing is that chemicals now have to come into play. Whenever chemicals come into play means that you are not really going to be dealing with a completely dry process. So, whatever are the difficulties with a wet process, those difficulties will have to be seen. Although final chemistry reactions may also take place quickly, but invariably the time requirements here are not going to be very easily comparable with the thermal system. So, you may have to be very choosy about things. So, let us for some time look at texturing of cellulosic spun yarn, which means cotton, viscose and such type of material. So, this is what it is, which we said we will use these materials and go by the process, except the difference will be here. So, as far as this is concerned, there are two basic strategies, they do not change. You can set by release of energy, or you can set by freezing in. So, the same thing that we discussed before will be valid here as well. Only thing that may change is which chemical, which solvent, what kind of things you will have. So, there were enough interest in textured yarn. Therefore, the earliest yarn which actually had the advantage of bulk and also stretch were the sheath core yarns. Earlier ones somewhere in 20s and 30s were elastics. So, where elastomeric yarn was in the core and the sheath was any natural fiber. And so, you get the aesthetics of natural fibers, because a spun yarn the bulk was definitely higher than a filament yarn and stretch was being given. So, this type of techniques are being used even today. So, wherever you have the sheath core system, so all the garments wherever they are supposed to fit snugly, let us say the upper part of the socks for that matter, they could be sheath core based systems. So, this is in some sense, you can always say much before the advent of synthetic fibers, you actually started enjoying the advantages of the bulk and also of the sheath. But because thermoplastic and thermoplastic yarns and thermomechanical texturing was attracting attention, and people wanted to use the natural fibers as well. So, introduction of thermoplasticity was also taken as a route to texturing. If somebody says, well, thermomechanical means can be used, then you try to introduce thermoplasticity to the yarn. So, that is like a chemical modification of the fibre itself. So, one can always say, well, this no more is cellulose as it is, but a modified version of cellulose, because you are not doing chemical modification. So, the plasticity, thermoplasticity can be introduced by blocking of hydroxyl groups. It is the hydroxyl group which are in abundance, for example, in cellulose, because of which you do not see thermoplasticity. When you heat, the intermolecular bondings are so strong that before any movement takes place between the molecules, the main chain starts degrading. So, it has been one of the principles that if you want the material to respond to heat, then you reduce the hydroxyl groups. How much? That we will call as a degree of substitution. This can be done by many means, you can do any kind of things, but esterification we already know. You have triacetate, diacetate fibres. So, you were doing the ester linkage was being introduced. So, depending upon what degree of substitution, the glass transition will keep coming down. So, in cotton you do not see glass transition, you do not see melting, you do not see glass transition. That means the molecules do not move with respect to each other because of heat. But when you start blocking them, hydroxyl group with the polar group are getting blocked. So, one, this bond cannot be, hydrogen bonds cannot be made. The distance between the molecules also starts increasing, and therefore, as you increase the temperature, kinetic energy can increase, and so you can see glass transition temperatures also, and that means thermoplasticity is being introduced. So, simple reactions like this can do, we are quite aware. So, people use the same process. The cellulose acetate was made by using a pulp and completely acetylation, and then you dissolve it and then make a fibre out of it. This is not the case here. You want the cotton to look like cotton, the spun yarn as it is. The chemistry was done in the spun yarn stage without destroying the yarn. So, you are only modifying part of the yarn. The yarn as a spun yarn will still look like a spun yarn, right. So, the trick is that you do not change too much first, change enough which can give you some response to heat, and therefore, this was one of the methods people tried to do chemical modification by blocking hydroxyl groups, first by esterification, which they were quite familiar with. Other is etherification, that instead of making an ester, you make an ether link, which also means that your hydroxyl group is not available as it is. So, for example, ether means you have two alcohols reacting with each other, and so you produce an ether link. From the point of view of stability of these links, ester links are more susceptible to alkaline conditions, ether links are more susceptible to acidic conditions. So, theoretically you can hydrolyze anything, but what we understand is that when you do normal washing, laundering kind of conditions that you give, whether these bonds are going to break, no, not very easily. So, based on this R, the size, the distance between the two adjacent molecules will be decided. Other than blocking, you have a steric moiety also, which takes space. So, if it is R is smaller or R is larger, the changes that you can expect in the properties of these fibers, let us say viscose or cotton, can be different. So, this is one of those things people know. Some of these compounds have also been used as thickeners. So, to get a methyl cellulose, so instead of taking an alcohol, you take a chloride, which means the reactions can happen at a temperature which is not too harsh. Like for example, if it is a methyl alcohol and you want to use cellulose and keep boiling it, you may find no ester group has generated, not whatever, and normally alcohols will boil before, evaporate before anything else happens. But the moment you add a chlorine group, the reactivity becomes quite high, and so in alkaline conditions you can expect an ether link being generated, which is called the methyl cellulose. That means, what will be the glass transition temperature, how much will be the change will depend on how many OH groups you want to block. So, stoichiometric reactions may have to be done to say if you block more, change will be more, if you block less, change will be less. Change definitely there will be. This is called carboxymethyl cellulose. Now, here instead of methyl you have a carboxymethyl group being added. So, the size is more, ether link still remains, and you are using a monochloroacetic acid. So, again you have a chloride of an acetic acid, which gives you a CMC, carboxymethyl cellulose. You can appreciate carboxymethyl cellulose also can be, sodium salt of the thing can be dissolved in water if you do good. It is used as thickener. So, if you do too much of this, then you will get a material which is changing so much, not just to heat, but it will respond to any aqueous solution making process as well. So, obviously, we do not want to go to that thing, otherwise no point. So, in every kind of a thing where you are looking a partial modification, but then you also are concerned as to how much reaction you must do and how much change you are going to get. So, what people did obviously was modify the cotton yarns and then take it to thermomechanical texturing process and get some effects, and which were permanent in the sense, whatever permanent means in this world, that during normal washing you would not see any change happening. If you remember, Haberlean process of viscose texturing involved only setting by steam. So, they are very happy about the process, but when you put it in water, all the new bonds, new hydrogen bonds made in different positions will get broken down and make bonds in a new position. So, all that effect would go, but if you do go by this process, effects will not go. How much will be the better effect would depend how much blocking you have done. So, that remains as a degree of substitution. So, one of the things which they found was quite successful in making textured yarns, this is also an ether link being created called the benzyl cotton. Using benzyl chloride, that they found that at a degree of substitution of 0.25. So, theoretically we could do 3 maximum. So, at a degree of substitution of 0.25, the glass transition temperature of cotton was found to reduce to 165. If you do more, it will go further down. Compared to a cellulose acetate, if you wanted that, if you want formula, you required almost 1.95 or more to get to 165 degrees as glass science temperature. And why? Because benzyl means there is an aromatic ring which is also getting attached, and therefore, distance between the molecules can be large, and so it became more effective, less change, but more effective. You go 0.5, maybe temperatures will come down further, glass transition temperature, and so some of the changes could take place. That is what there. So, they found etherification by using benzyl chloride was an effective way to modify cotton to be good for using finally thermomechanical means for texturing. You can appreciate the kind of expectations that you have with a multifilament yarn were not there here. This any spun yarn is much more bulkier compared to a multifilament yarn. So, they were already bulk. Now, if you increase any further, everybody liked it, but more than that, the stretch that comes. So, as long as the setting is okay, optimized, then you could get. So, this is how people were working on that. Means that the textured yarn and the properties thereof were of considerable interest to the people. So, I mean other methods were also tried, not really so successful, like cyanoethylation of cotton also could introduce thermoplasticity. Other process people tried was called in the principle called crystallization, decrystallization, or in the other way, if we say decrystallization and recrystallization. It is something similar to melting or a partial melting. In partial melting, as we say thermomechanical systems also, we said partially it will be decrystallized and then recrystallize. So, you have crystallization decrystallization processes going on. If that can be done by chemical means, it should again lead to a setting. So, crystallization decrystallization process was tried, and what do you do there? You need a solvent. It is not easy to dissolve cotton, difficult solvents are being used, therefore, it is stable. Sodium hydroxide solutions, mercerizing caustic, it withstands. Clear boiling for hours, 10 hours together withstands. So, the normal common systems are, it is much more stable, and that also just in a way proves that the so called ether link and the intermolecular hand bonding is strong enough. So, solvents are required. So, one of these solvents, if you are aware, was called a cupra ammonium hydroxide. How many people have heard of this solvent? So, what does it do? What do we do with this now? What do we do with the solvent? So, one is the rayon itself. So, there were two processes which are being followed, which were being followed in earlier days. One was a xanthate process of dissolving the cellulose first, modifying and dissolving, and then regeneration. Otherwise, direct solubilizing using cupra ammonium rayon. Copper and ammonium, this hydroxide is a complex which is very delicate complex. Change of a bit of a temperature here and then the gas would go, and you will find this is not more effective. But even today this cuprum hydroxide solution is used to determine the fluidity of cotton or cellulose. Fluidity is inverse of viscosity, right. When you do scouring, when you do bleaching, there is degradation of the molecule. So, people like to know how much molecule has been degraded. So, if it degraded more, fluidity is more with the same concentration. So, this can be used, but again people found it is difficult to handle this solvent for a process for modification. Then they found another inorganic compounds like zinc chloride at different aqueous concentrations. This can be act like a solvent. Solvent means that it would be able to separate the molecules without degrading. Sulfuric acid can do the same thing. If you do a concentrated sulfuric acid, cotton will become completely solubilized, but you will not be able to get back anything because the main chain also has been broken down. It is like going for a flaming portion, heating, going to temperatures of 200, 550, 300 degrees centigrade, the degradation is permanent. But these type of solvents at certain concentrations can act like true solvents. Without degrading thing, they can break down the intermolecular hydrogen bonds, they can work at the crystalline region, decrystallize. So, if you treat with this, the crystallinity of the compound material will go down of the cellulose, and again can be recrystallized. Things like ethylene diamine, they are also considered to be good solvents. Tetraethyl ammonium hydroxide TEA is also a good solvent, and they are not as delicate as cuprammonium hydroxide, and they have been also tried to do the texturing. Now, in this case you are dependent only on a solvency property and not introduction of thermoplasticity. In the first case, you were first introducing thermoplasticity and then using thermal means to do the texturizing. In this case, you are using this solvent to do exactly what you were doing as a partial melting and recrystallization. So, decrystallization and recrystallization using these solvents obviously optimize, and then you can remember here, like during heating, melting and recrystallization both take place. Similarly, during solvent absorption, decrystallization and recrystallization can also take place, because crystallization is still a thermodynamic process. If you give opportunity, molecules will like to crystallize. So, you can have a complete solution through which crystallization will take place. If that was not true, you would not be able to make solution spun fibers, they all crystallize. So, it is akin to melting process, melting recrystallization, partial melting recrystallization. So, you have partial decrystallization and recrystallization. So, this is the process which the solvents follow, and expected the people who were working on these found the crimp rigidity of the textured yarn obviously was influenced by the extent of decrystallization and recrystallization. The process optimization for the same kind of solvents with viscose versus cotton will be different, because cotton is more crystalline compared to viscose. So, difference is almost about 20% or more, and so optimized temperatures, more than temperature, let us say time, would be different. So, ethylene diamine is an organic system. And triethyl ammonium hydroxide is obviously an ammonium compound. So, ammonium compounds are 4 linkages, therefore, they get a positive charge. And an hydroxyl group which may be associated with this. So, is an ammonium salt. So, they can also break quite effectively the intermolecular hydrogen bonds within the crystalline region also. So, they have been used for decrystallization recrystallization process to get a textured yarn of cotton and viscose. So, it is just showing that there have been enough interest for people to keep working. So, interfacial polymerization of the yarn, spun yarns, let us say cotton, will also been attempted. But this is different than introduction of thermoplastic by chemical modification. Here there is no chemical modification, it is only deposition of the polymer on the surface. So, this was found to be one of the easier techniques to get a layer of thermoplastic material on a fiber surfaces. Have you heard of Verlan process? How many? What is it?
To reduce the scale of wool on the surface of
All right. So, this process has been used to mask the scales on wool. So, we know woolens have the process in which you call the shrinking takes place because of felting, and which is because of the scales that you have on the surface. So, that is directional frictional effect as they call them. And the only way to avoid this was either remove the scales by mechanical or a chemical process, or cover them up by a polymer. So, Verlan process used interfacial polymerization method to coat the fibers. A similar process was tried for texturing also, and they called it a polyamide process. Because you were generating a polyamide on the surface. So, if you have adipic acid and hexamethylene diamine, if these two things are there, what do they give? So, they give nylon 6,6, and you know how the nylon 6,6 is polymerized. It is polymerized at a very high temperature pressure conditions, right. But in case instead of using adipic acid, you use adipoyl chloride, reaction can take place instantaneously at room temperature, just like that. That is what is interfacial polymerization. So, interfacial polymerization, the reactants are highly reactive. So, making a chloride of an acid can give you a very highly reactive compound. So, normally what would happen is that if you have two solutions and you have one reactant here A and the other as B and highly reactive, and if there is an interface, let us say one dissolves in organic solvent, the other dissolves in aqueous systems. So, interface, they do not mix, they come in contact only at the interface and immediately polymerization takes place, and that is what is called the interfacial polymerization. So, what we people do, adipoyl chloride is reactive and goes in organic phase, heptanes, hexanes, so on so forth, and hexamethylene diamine can be in aqueous phase. So, you can pad a sheet of yarn through hexamethylene diamine and then let it again, after padding, squeezing, let it go through the adipoyl chloride, immediately there will be a polymer formation on the surface as it is passing. This reaction is very quick at room temperature, and then of course, you can wash, dry, whatever. That means you have a thermoplastic layer, nylon or polyamide is a thermoplastic layer. You can use this. So, theoretically any acid chloride can be used. This is a 6 membered carbon, you can have a 10 carbon like a cibocoil chloride, different kind of polymers can be made. Verlan process used a nylon 610 to get this polymer done. So, you can use any one of them. So, this type of a process which has been used with other polymers or monomers also, like isocyanates. You heard about isocyanate somewhere? How do you, where have you heard about isocyanate? Do you have any story on that? Right. So, it is a disastrous kind of thing. It is disaster because it just, the moment it looks at the hydroxyl group, it reacts. You see a water, it just reacts, doesn't wait, so quick. So, you have to really contain it. So, working with isocyanates can also be done, polymerization can be done. You can make polyurethanes, polyurethanes are being made now also. You have to be very, very careful when the reactions takes place. After reactions take place, polymer is relatively more safe, right. The monomer is very, very active. So, acid chlorides like adipoyl or isocyanates can be very reactive compounds which can participate in interfacial polymerizations. And that means you can coat the material and then use the thermal means. So, the other thing you can see that the cotton and cellulose had attracted attention of the researchers so much that many methods have been tried. Finding that this is not a thermoplastic material, what do we do? So, this is what people started doing it. They finally, what is called a covalent cross-linking, that you, this is different than what has happened before, that you are actually making a covalent cross-link between the molecules rather than breaking anything, so adding things. And so, this employs definitely a principle of freezing in. So, this could be done with the multifilaments also viscose, which we said sometimes you could do. It can be done with the cotton, viscose, staple fibers as well. It can be done on wool also, in case you have a nice kind of a cross-linking agent which can link with wool or a silk. Any material where you can produce a cross-link, covalent cross-link, and covalent cross-link obviously is much stronger than any hydrogen bonds. If that happens, then the effect that you will get is going to be permanent. Permanency, as we said, is a relative term. So, we can stop here and continue from here further.